Okay, so in this video we are going to work with the product and quotient rules. We already saw in the flip class video what these rules are, but let's go ahead and recall these. So let's start with the product rule. So this is going to allow us to take the derivative of products of functions. So if I take two functions f and g and I take the derivative, this is the derivative of the first function times the second plus the first function times the derivative of the second. So let's go ahead and see kind of where this comes from. We didn't talk about where this comes from at all in the flip class video. So we would know from the definition of the derivative that this should be the limit as h goes to 0 of fg of x plus h minus fg of x over h. And we can rewrite this as the limit as h goes to 0 of f of x plus h, g of x plus h, minus f of x, g of x over h. And so now let's take a look at this quantity we're taking the limit of here. And let's look at this geometrically to see what this is giving us. So let's start by thinking of drawing a box here. And let's suppose this full distance here is f of x plus h. And this distance here is g of x plus h. So what we can think of is we had some distance length here that was f of x. So say this distance is f of x, and then we had some distance that was g of x. So let's say this distance is g of x. And then as we add a little h to it, we get a little bit more. So now if we think of what this area here is in the green, so this green area, this is f of x times g of x. And then the entire area, if we include all of it, the orange is f of x plus h times g of x plus h. So if we think of, so we're looking at what the difference here between those is. So if I look at f of x plus h, g of x plus h minus f of x, g of x, if we redraw this picture here, so this is all of the orange area is f of x plus h, g of x plus h, and then we want to subtract the green area. So that tells me what I'm looking at then is this area here. And so if we think of this, really what we have for that little area then is this part here. This is f of x plus h minus f of x. And this part here is g of x plus h minus g of x. And then this length here is f of x. And this length here is g of x. So if we were to say this part right here, suppose we ignore this because it's going to, as h gets small, that's going to get small. Then what we would have is f of x plus h, g of x plus h, minus f of x, g of x, let's say over h, is approximately, well, the area of each of these red rectangles here. So it's going to be g of x plus h. Well, let's start with the f's instead so it matches the formula above. So f of x plus h minus f of x times g of x, that's this red rectangle here, say over h, plus g of x plus h minus g of x times f of x over h, and that's this rectangle here. And so we can say the limit then is h goes to 0 of these things, we're going to say that little blue box above goes to 0, so we'll just say these are equal. I wrote that down wrong. And now notice we can pull the terms that don't have anything to do with h out front. So I'll have g of x times this limit and then we can recognize these as the derivatives. So that's where our product rule comes from if we want to think about it geometrically. Of course, if you want to just memorize it, that's fine too, but that gives you an idea when you can think back of, well, you're really just looking at these kind of red rectangles as the difference of what's changing when we change x by a little bit for the product of a function. So let's try some examples on how to actually apply this. Okay, so here we have a product of two functions. So we can say this function here, we can call that f of x, and we can call this g of x. And so now, for the product rule, I know I'm going to need f prime of x, which is negative sine x. I'm going to need g prime of x, which is going to be 5x to the fourth minus 7 minus 1 over x squared. So the product rule says that the derivative of h should be the derivative of f times g plus f times the derivative of g. And now since we've taken these derivatives, we can just plug these in. So the derivative of f was negative sine x, and then we just stick g in there with no changes, and then we put f in there with no changes, and now put the derivative of g in there. And that's our derivative. So let's try another example. So let's let f of x be x cubed plus 7x minus 2, and let's let g of x be given by the following graph. So let's say it starts here. It's a line, it's going to start there, go through that point, and then it'll go up. And don't worry about the tick marks on the rest of it, because I wasn't so careful on doing those. But we know it goes through the point 0, minus 2, and 1, 0. So let's find the derivative of f times g at the value x equals 2. So again, we know fg prime at 2 is going to be f prime at 2, g of 2 plus f of 2, g prime of 2. So the first step here might be to find the equation of g. So let's find the equation for y equals g of x. So we know it's a line through the point 0, minus 2, and 1, 0. So that means our slope here, we can take change in y over change in x. So it's 2 over 1, so this is 2. And so that also, notice, immediately tells you g prime of everything, since it's a line, is 2. So in particular, g prime of 2 is 2. And then for g of x, we can use point slope formula. So we can do y minus 0 is equal to 2 x minus 1, or y equals g of x is 2 times x minus 1. So if I plug in 2 to this, I should get 2 times 2 minus 1, which is 2. And then for my f up here, I have f is, maybe let's copy it down here again so we have it in front of us. So this is x cubed. And then we have plus 7x minus 2. So f of 2 is going to be 2 cubed plus 7 times 2 minus 2. So this is 8 plus 14 minus 2. So this is 20. And f prime of x is 3x squared plus 7. So f prime of 2 is going to be 3 times 4 plus 7. So this is 19. So fg prime at 2 is going to be f prime at 2, which is 19, times g of 2, plus f of 2, which is 20, times g prime of 2. And so this is 38 plus 40, so 78. Okay, let's try another example. So for what intervals? Is f of x being x times e to the x concave up? So maybe we start by recalling what concave up means. So concave up means that the second derivative is bigger than 0. So that means we need to take the second derivative of this function. So we use product rule, so it's going to be the first function times the second plus the first function times the derivative of the second. So this is 1 times e to the x plus x times e to the x, which is e to the x times x plus 1. And now we need the second derivative, so same process. Derivative of the first function times the second. Notice it doesn't matter which order we write the function for this. And so this is e to the x times x plus 1 plus e to the x times 1. So this is e to the x times x plus 1 plus 1, which is e to the x times x plus 2. So that gives us our second derivative. And now note, for concave up, we want the second derivative to be bigger than 0, which is the same thing as e to the x times x plus 2 to be bigger than 0. Okay. So we know that e to the x is bigger than 0 for all x. So the only way for this to not be bigger than 0 is if x plus 2 is less than 0. So we want x plus 2 to be bigger than 0. Well, when's that true? This is true when x is bigger than negative 2. So our function is concave up on the interval from minus 2 to infinity. Okay, so let's try one more example with product rule before we move on to quotient rule. So let's try word problem. Okay, so the quantity of a certain skateboard, the number that we sell, depends upon the selling price P in dollars. So let's write this in terms of a function as Q is equal to F of P. We're not saying what F is. It's just we just know it is a function of the price. So let's suppose we know that F of 140 is 15,000 and F prime of 140 is minus 100. So let's answer a couple of questions about this. So for the first one, say what do F equals of 140 equals 15,000 and F prime of 140 equals minus 100 tell us about the sales of skateboards? Okay, so remember that what we're plugging in here is the price, so that 140 goes with the price. And for the regular function, this is just the quantity. So F of 140 equals 15,000 means if the price is $140 for a skateboard, we will sell 15,000 of them. Now, the derivative is telling us if we change the number or the price of the skateboards, how will it affect the number? So F prime of 140 equals minus 100 says, or tells us, if we raise the price by $1 to $141, we will sell about 100 less skateboards. Right, that we can think of, remember, the units of F prime are quantity, so number of skateboards over the price in dollars. Remember, writing that down can sometimes help with the interpretation. So if we sell 100 less skateboards, so it would be about 14,900 skateboards. If the price is $141 for a skateboard. Okay, so that's our first question. Second one, let's say the total revenue are earned by the sales of skateboards is given by R is equal to the price of them times the quantity sold. So let's find dr dp when P is equal to 140. So the first thing to note is we can write R, this is P times Q, which is P times f of p, because q is equal to f of p. So in particular, if we take the derivative of this, we're using the product rule. So this is the derivative of the first times the second plus the first times the derivative of the second. We know the derivative of p with respect to p is just 1, so this is just f of p plus p times f prime of p. So now I want this when p is equal to 140. So this should be f of 140 plus 140 times f prime of 140. And now we can fill in these values. This was 15,000 plus 140 times minus 100. And so this is 1,000. So in particular, we see the change in revenue. This is positive. So it is an increasing function. So at, this is when p is equal to 140. So at p equals 140, revenue is still increasing. Right, so in particular, this shows us that even though the number of skateboards we'd sell is less if we increased the price, the overall revenue would still go up. And that's because we're selling enough of them so that the higher price makes up for the loss of revenue of the actual skateboards. Okay, so now let's move on to the quotient rule. So let's recall this from the flipped class video. So for this, if we take the quotient of two functions and take the derivative of that, it's the derivative of the top part times the bottom minus the top part times the derivative of the bottom, all over the bottom term squared. So we're not going to go through an argument for why this is true. So for this one, it's probably best to just memorize it. You'll do enough examples where that should help you memorize it. So let's try an example. So let's look back at our trig functions, and let's let h of x be tangent of x. So we saw before what the derivatives of sines and cosines are. Now we can get the other trig functions by using the quotient rule. So let's write tangent of x. Well, we know that this is sine of x over cosine of x. So if we were to set f of x to be sine x and g of x to be cosine of x, then we can use quotient rule to say h prime of x. This is f prime of x, g of x, minus f of x, g prime of x over g of x squared. I know that f prime of x is cosine of x, g prime of x is negative sine of x. That's from our work before on derivatives of trig functions. So this thing becomes cosine of x, and then g is cosine of x, so another cosine of x, minus, and I have sine of x times negative sine of x, all over cosine of x squared. And now we can simplify this, so this becomes cosine squared x. Notice those two the negative signs cancel, so I get sine squared x all over cosine squared x. The top part just becomes 1 from our Pythagorean identity. So we get 1 over cosine squared x, which is just secant squared x. So another one to add to our library of functions that we know the derivatives of is the derivative of tangent is secant squared. So for this one, I would encourage you, don't bother memorizing this. You might use it enough that you end up memorizing it inadvertently, but just know how to use the quotient rule to get this. It doesn't take very long to go through and derive it rather than trying to memorize the whole thing. Okay, so let's try another example. So let's let f of x be e to the minus x. And so let's find the derivative of this. So we know the derivative of e to the x, but we don't know e to the minus x. But what we can do is we can write e to the minus x as 1 over e to the x. And now we can use quotient rule. So that means f prime of x is the derivative of the top part times the bottom minus the top part times the derivative of the bottom all over the bottom squared. And now we know the derivative of 1 is 0, so this is 0 times e to the x minus the derivative of e to the x is just e to the x all over e to the x squared. So this becomes minus e to the x over e to the x squared. And now we cancel one of those e to the x's, so I get minus 1 over e to the x, which I can write as minus e to the minus x. Okay, let's do another one. Okay, so let's find the equation of the tangent line at x equals 1 to this function f of x is equal to 3x squared over 5x squared plus 7x. So the first thing to note is we can simplify this a bit away from x equals 0. So notice I can write this as 3x squared over x times 5x plus 7. As long as, well, we can write it like that for everything. But then we can simplify this by canceling an x and writing it as 5x plus 7, as long as x is not equal to 0. And since we're interested in the tangent line at 1, that's going to be fine. And it's not a big deal. This just saves a little bit of work for us. So to find the tangent line, we need a point on the line and we need the slope. So let's start with a point on the line. So let's evaluate this at 1. So we get 3 over 5 plus 7, which is 3 over 12, which is 1/4. So our point on the line is 1/4. And now we have to find the slope. So to do that, let's take the derivative. So this is the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. And now these are just lines on the top that we're taking the derivative of, so these are nice and easy to differentiate. So if we simplify this a bit, we can write this as 15x plus 21 minus 15x all over 5x plus 7 squared. Cancel those 15x's out, and I get 21 over 5x plus 7 squared. So that's the derivative of f everywhere except for This is again for x not equal to 0, because we have to be careful because we use that other version of the function. So now to get the slope of our tangent line, we have to plug in the value for x. We plug in 1, I get 21 over 5 times 1 plus 7 squared. So I can think of this as 3 times 7 over, now this is 12 squared, so this is 3 squared times 4 squared. So if we simplify this, this is 7 over 48. So then our tangent line, well, we use point slope formula, so y minus 1/4 is 7 over 48 times x minus 1. Okay, let's go ahead and try a word problem now. Okay, so we have an electric current passing through two resistors with resistance R1 and R2. These resistors are connected in parallel. And in this case, the combined resistance, which we'll denote by big R, can be calculated from the equation 1 over big R is equal to 1 over little r plus 1 over little r2. Okay, so let's find the rate at which the combined resistance changes with respect to changes in R1 if R2 is held constant. So we're only going to change the resistance of one of the resistors. Okay, so let's just note what we want to find. Well, I want dr over dr1. So that's what we're looking for here. So to do this, I need to rewrite this equation here, star. We need to solve that for r. So what I can do is multiply both sides by r to get this equation, and then divide both sides by the 1 over r1 plus 1 over r2. So I get r is equal to 1 over 1r1 plus 1 over r2. And then let's go ahead and multiply the top and bottom of this by r1, r2 over r1 over r2, which is just multiplying by 1. So you get r1, r2 on the top. And then when I FOIL this to the bottom, I'm going to get r1, r2 over r1, 2 over r2. And then if we simplify that, we get r2 plus r1. So to get it all in one spot, this is our equation for the combined resistance. And now we're in a position where we can use quotient rule to take this derivative. Remember, R2 is being treated as a constant, so this is the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. So since R2 is a constant, the derivative of R2 times R1 is just R2. Right, so you're thinking of, so for this derivative here, you're thinking R1 is kind of x and R2 is some number. So if you had like 5 times x, the derivative would just be 5. So in this case, R2. The derivative of this part will just be 1 plus 0, because R2 is constant, all over R1 plus R2 squared. And now we want to simplify this, so I'm going to get R1 R2 plus R2 squared minus R1 R2 all over R1 plus R2 squared. You see we get cancellation there, so I get R2 squared over R1 plus R2 squared. And that gives us our answer. Okay, let's try one more example in this section. So let's work with some graphs again. So let's consider so I'm going to put these two functions here on the same graph. So for this one, we're going to start here and go all the way down. So think of this as just a line. Y equals g of x for this one. And for this one, we're going to go, let's say, up here, 2, 4, and then down like this. It's f of x. So those are our functions. And so what do we want to do with these? For the first ones, let's set h of x to be f of x over g of x, and let's find h prime of 1. Well, we know h prime of 1 is f prime of 1, g of 1, minus f of 1, g prime of 1, over g of 1 squared. So looking back up at our graph, we're going to need to find equations for these. So let's start with g of x. So notice this goes through the point 0, 4 and 4, 0. So the slope for this one, we could say 0 minus 4 or 4 minus 0. So this is negative 1. So I can have y is equal to negative 1, x minus 4. And that would be equation for that. So g of x is equal to negative x plus 4. So that can get me we'll come back to that in a second. And then for f, we need the part where it's 1, so we're looking here. So we want the left part of that. So let's go down here. Let's write down our g. Let's write our g down here. So g of x was equal to 4 minus x. And now for f of x, we know this goes through the point 0, 0. And it goes through the point 2, 4. So that means my slope here is 4 minus 0 over 2 minus 0, which is 2. So my equation can be just 2x here using the point 0, 0. So we can see g of 1 is 4 minus 1, which is 3. G prime of 1 is just negative 1. That's the slope of that line. F of 1 is 2, and f prime of 1 is 2. So if we look back up here at our equation, this is going to be 2 times 3 minus 2 times negative 1 over 3 squared. So this is 6 plus 2 over 9, which is 8/9. So really for this one, it's just a matter, we know the quotient rule here, but then we need to find the equations of the relevant lines here. So for the second one, let's let m of x, now let's do g of x over f of x, and let's find m prime of 3. So let's start by writing our equation using quotient rules. So this is going to be the derivative of the top, which is g, times the bottom, minus the top, times the derivative of the bottom, all over the bottom squared. Now we know that g is just one line during the whole thing, so we already know what that equation is. It's 4 minus x. However, since we're looking at 3 now we need this part of f of x. We need this other term for f of x because it's two different lines. So in this case, we're going through the point 2, 4 and the point 4, 0. So for this line, my slope is 0 minus 4 over 4 minus 2, which is minus 4 over 2, which is negative 2. And so for my point slope formula, I can do y minus 0 is negative 2 x minus 4 using this point here. So f of x for this part is 8 minus 2x. And so now we can fill everything we need in. So g of 3 is 4 minus 3, which is 1. We know g prime is always minus 1. F of 3 is 8 minus 6, which is 2. And f prime of 3 is negative 2. So now we can fill this in above. So this is negative 1. And then f of 3 is 2 minus, and then I've got g of 3, which is 1, and f prime of 3, which is negative 2, all over f of 3 squared. So this is negative 2, and then I get plus 2 over 4, so this is 0.